So I am super excited. This presentation is going to be fantastic. Mr. John Saltenberger is here with us. He's a meteorologist. He's got 40 years worth of weather forecasting experience, starting through his early work with NOAA, the National Weather Service, and his current work with the U.S. Fish and Wildlife Service. He's currently serving as fire weather meteorologist at the Northwest Interagency Geographic Area Coordination Center in Portland. John has experience providing weather support for wildland fire managers in the U.S. and in Australia. As a NWS employee, John spent 17 seasons as an incident meteorologist, working in the field and deploying firefighting teams across the U.S. Hugely important these days. John has presented classes and workshops on topics such as fire behavior, fire weather, and fire danger throughout his career. John's a published co-author and a teacher at Clackamas Community College. John will be referring to handouts during the presentation. They were emailed twice to the listserv, once on August 9th by Mark Neiman-Ross, and then Monday on the 25th by Jim Mernick. So check the listserv for those handouts. There's a couple hard copies up here that John brought with him. Also, please save questions till the end of John's presentation, because most likely he'll answer your questions that you have in your head. So hold those questions. People in the Zoom, put your questions in the chat. And without further ado, here is John Saltenberger.
All right, so I will try to take questions at the end, although I usually welcome questions during the presentation. But at the end, I'll do my best to avoid your questions as best I'm capable. All right, so yeah, thank you for the kind intro. I enjoy presenting topics in meteorology. This presentation tonight is adapted from several that I have given to various levels of wildland firefighters. I work in a center that's tasked with anticipating fire conditions across Oregon and Washington. A big part of that is thunderstorms and lightning, which you've clearly seen over the past few days or so. We'll elaborate on that topic. So let's move one forward. All right, very good. So let's do some fun facts about thunderstorms on the globe. At any one time, okay, so at any one time, there are about 1,800 to 2,000 thunderstorms ongoing around the surface of the globe at any time. So there's a constant flow of electricity from the atmosphere to the earth, or vice versa. There's an electric charge in the atmosphere. Thunderstorms help amplify that electric charge. They also help decrease that electric charge based upon the distribution, which we'll talk about. In the United States, there are about 100,000 thunderstorms that occur across the U.S. on an annual basis. Some years a little bit more, some years a little bit less, but it's a fairly constant number. And of those 100,000 thunderstorms, about 90% of them or so, the typical life cycle is only about 30 to 45 minutes or so. They're not really long-lived beasts in most cases. There are some exceptions to that. And the typical thunderstorm diameter is about 15 miles or so in diameter. Let's bump forward one slide. Okay, so thunderstorms per year, the number of thunderstorm days that happen in any given year on average across the United States. This is broken out in thunderstorm days per year. So we can see right away by looking at this graphic, where is the hot spot for thunderstorm activity? Hit one slide. Let's go forward one. There we go. Florida Peninsula, particularly on the Gulf side of the Florida Peninsula, has over 100 thunderstorm days per year, which is basically every third or fourth day in Florida on the Gulf side, there's a thunderstorm going on. And then the frequency of thunderstorm days per year decreases as you go to the north or to the west, and it decreases bit by bit until you get all the way out to the West Coast. If you like thunderstorms, the Pacific Coast is the worst place to live, because we only get about 1 to 2 to 3 to 4, 5 thunderstorm days per year on a good year along the West Coast. Let's go forward one slide. Okay, so let's do a comparison. Miami, roughly 100 thunderstorm days per year. San Diego, at roughly the same latitude, gets only about 5 thunderstorm days per year. Why the difference? Why the difference between the two? They both get about the same amount of sunlight. energy from the sunlight. Let's bump forward one slide. Okay, so the difference is one more slide. We need to have several ingredients to get a thunderstorm going. You've got to have moisture. You've got to have a lifting mechanism to lift that moisture upward. And then you have to have an acceleration mechanism, and that's called atmospheric instability. All three are necessary to get thunderstorms going and sustain them. The more optimum the combination of those three contributing factors, the stronger the thunderstorm is most likely to be. Let's go forward one slide. Okay, so those thunderstorms require one, go ahead, one forward. Moisture source, one forward. Now, both San Diego and Miami have moisture sources. They're both located next to big oceans. So proximity to an ocean isn't necessarily the ingredient of the difference in thunderstorm frequency. Let's go forward one more. We have to have lifting mechanisms as well. Let's go forward one more. San Diego and Miami both have atmospheric lifting mechanisms of various types, but they're both there, so they contribute. One more, atmospheric instability. Let's go forward one more. Miami has atmospheric instability. San Diego doesn't. All right. So if you ever look at cloud patterns in Florida, they go up, cumulus clouds. If you looked at cloud patterns in San Diego, they go flat, they go sideways. They're stratus type clouds. The differences between the two, this ingredient called atmospheric instability. Let's go forward one more. Atmospheric instability in a nutshell, and it's a big topic, is high amounts of water vapor concentrated in the lower atmosphere. Through the depth of the atmosphere, not so good. High amounts of water vapor concentrated in the lowest atmosphere, say the lowest mile or so of the atmosphere. That's where you concentrate your moisture. That's where you concentrate your heat. That's where you concentrate your energy. That's a big part of atmospheric instability. And then the other part is unusually cool temperatures in the upper atmosphere to balance that. We get a contrast between warm and moist below, cool and dry above. That's what creates atmospheric instability, because the atmosphere does not like big differences in temperature or density, and it will act to reverse that. That causes warm, moist updrafts that rise rapidly. One forward. So atmospheric instability is realized by taking that warm moisture in the lower atmosphere, hoisting it upwards, so that lifting mechanism, and that releases all the energy that causes thunderstorms to occur. Let's go forward one. So based upon that, warm, moist conditions in the lower atmosphere, it should come as no surprise that the global hotspots for thunderstorm activity is near the tropics, near the equator, because that's where the moisture is, and that's where the heat is in the lower atmosphere. Miami is just a toehold into that. You really want to see thunderstorms and atmospheric instability, go to Central Africa or Central South America or Borneo. You'll see some thunderstorm activity even more than what you find in Florida. So that's where the energy is, that the heat and the moisture combine to create that uplift in atmospheric instability. Let's go forward one. Okay, let's talk about the subset of storms, thunderstorms that become severe. All right, there's all thunderstorms, and then there's a smaller subset that are severe, and that is roughly about 10% of the storms that happen over the United States are classified as severe. Let's go forward one. A severe thunderstorm is defined as a storm that creates hail of a half-inch diameter or more, winds of 58 miles per hour or more, and or a tornado detected. Any of those will qualify a storm as being a severe thunderstorm. So one of the things the National Weather Service does is they track all thunderstorms that occur, but they also track that category, that proportion of storms that reach severe category, because that's one of the things that they're trying to forecast with their watches and warnings for tornadoes and severe thunderstorms, is like separate out the average thunderstorms from the bad ones, or they're trying to separate out the black bears from the grizzly bears. All right, so that's what they're looking at. So let's go ahead. So of severe thunderstorm frequency, go ahead and hit one. We know that the most thunderstorms occur over the Gulf Coast of Florida, the greatest number of thunderstorms. But the worst thunderstorms, the greatest frequency of thunderstorms that become severe, one more, is that, you guessed it, over North Texas and Oklahoma, right around the Red River. If you've ever been there, That is probably the most violent area on Earth for changeable weather and severe thunderstorms because of the unique geography of North America. And for reasons we could spend a lot of time going into, that's a place they call Tornado Alley. That's where the clash of air masses and moisture and lift and instability and all those things I've been talking about, that's where they occur most frequently and most severely, is in that spot right there. So let's go forward one. Okay, one more. Okay, so thunderstorms require a moisture source. Go ahead, one. Oklahoma is not near an ocean. It's well inland. So proximity to an ocean is not a guarantee of severe type thunderstorms. Big ones, wet ones, sure. Severe type, not necessarily. You got to get away from oceans to get severe thunderstorms. Next one, lift mechanisms. Next one. Oklahoma has better lifting mechanisms than Florida. They both do, but Oklahoma gets them more frequently, lifting mechanisms. One more, atmospheric instability. One more, yeah, Oklahoma has more atmospheric instability than Florida does. So the combination of these contributing factors becomes, even though Oklahoma is inland, it becomes more severe over Oklahoma. The optimum alignment of critical conditions occurs most frequently over Oklahoma. Can occur elsewhere, but that's the number one hotspot, Tornado Alley. All right, let's go forward one. Let's talk about the life cycle of thunderstorms. All thunderstorms, even the biggest, baddest ones, start off in a small stage, then a medium stage, and then a final stage. Let's go through each. The first stage is what's called the towering cumulus stage, or also called the developing stage, or sometimes it's called the cumulus stage. And that's just an innocent, puffy little cumulus cloud, but we saw a lot of those today, that build upwards. Some of them get bigger and stronger, and those go to the towering cumulus phase. So that's what we're going to look at. Let's go forward one. So the characteristics of the developing stage or the towering cumulus stage, the first stage of thunderstorm development, begins with towering updraft and cumulus clouds. And I will emphasize it's updrafts only in the updraft and cumulus stage. It's just energy feeding into that thing from below, helping it billow upwards. At this point, there's little, if any, rainfall coming out of it for reasons which we'll see here shortly. And it only lasts about 10 minutes or so. And that puffy little cumulus cloud that starts as a little piece of cotton in the sky to something that becomes big and nasty, it can happen in a short period of 10 minutes. And in the cumulus stage, very rarely we get a little in-cloud lightning. Boom, a little flash, not too much, just a little bit. Let's explore that a little deeper. Next slide. So there we are. There's the towering cumulus stage. You can see it's got more updraft energy than the typical cumulus cloud. It's billowing upwards. In fact, not only is it billowing upwards, it's accelerating upwards at this point, gathering energy, gathering momentum, and going straight up. Next slide. Okay, so in that towering cumulus stage, in a motion loop, I really love time-lapse photography because you can really see the development and decay of clouds. That's the towering cumulus stage. You can see it's billowing upwards and then it collapses. It billows upwards and it collapses. It hasn't got quite all its ducks in a row yet. All right, it's still gathering energy. So that's the towering cumulus stage. One more. So in the developing stage, the towering cumulus stage, it's updrafts only. As that cloud billows upwards, it's carrying all this heat and moisture upwards with it. There's condensation of water droplets inside that cloud as it billows upwards. It's cooling off as it gets higher and higher, and the cooling causes condensation and droplets appear. Go ahead and hit the next slide. Because the updraft is so strong, the droplets actually get suspended and lifted inside the towering cumulus stage. All right, the raindrops, they want to do their thing and fall out of the cloud. The updraft is too strong. Not only is the updraft strong, it's accelerating upwards at this point. And that's what atmospheric instability does. So the cloud droplets and rain droplets and hailstones and other frozen items are suspended and moving upward in that cloud. All right, the crowd asked, John, how strong do the winds get in an updraft stage of a thunderstorm?
Really strong.
Really strong. Let's find out. 100 miles per hour or more, going up, straight up, inside there, all right? How strong? Let's go to the next slide. So this was a paraglider, a Polish paraglider, who was competing in Australia, in a paragliding competition to see who could go the highest and the farthest and the longest, jumping off a hill in Australia and riding the currents of air and see how high, how far, and how long they could fly in the sky. She found it, all right? Because what happened to her, she got sucked into, her and other competitors were circling around underneath a billowing cumulus cloud in the developing stage, circling around, catching the updrafts and riding it just like birds, except that the updraft accelerated updraft, created a vacuum and pulled her and other competitors into the cloud, billowed upwards. So go ahead, one forward, swept her upwards in a rotating column inside that billowing cumulus cloud up to 32,000 feet inside the center of the cloud. That's how strong and how high the instability is in the atmosphere when all the ingredients are in place. Go ahead one forward. She went above the limit of human oxygen. She passed out inside the cloud and she lost control of the paraglider. And she was buffeted around inside the cloud because it's so turbulent, so energetic. Raindrops were falling, hailstones were hitting her. Her body was in flight suit were coated with ice. In fact, they believe that she had like an inch of ice coating in her entire body on her flight suit. And that's what saved her life, because as she swept up to above 32,000 feet, the temperatures up there were 50 degrees below zero with very low oxygen content. And the whole time, go ahead and forward one, she was still wearing her GPS the whole time. So it's tracking everything that's happening to her as she's passed out and just billowing inside this turbulent, violent. She's battered with hailstones, coated with rain and ice, lightning strikes going on inside the cloud. Her canopy is getting shredded, really bad circumstances. Let's go ahead one more. She did. She did win. She drifted 40 miles unconscious and finally came down to about 15,000 feet where it started melting. Her flight suit started melting and she regained consciousness and was able to bring her paraglider back down, and her chase crew was following her and they were able to recover her. Frostbite, hands and ears and hands, but survived. And yes, she did win the competition. And they could not believe, what happened to her. There was another pilot, a Chinese pilot, lost her life inside the cloud because of the severity of the conditions. So that's how strong the winds get, updraft winds inside the developing stage of a thunderstorm. Let's go forward. So that's what it looks like in profile. It's all updrafts. There's condensation of moisture droplets, but it's all getting pulled upwards by the strength of the heat being released by the condensation. Imagine like a boiling tea kettle. All that energy is coming out of that thing and going up. That's what's happening here. All right. So it can penetrate tens of thousands of feet up into the atmosphere. Let's go forward one. We reach the next stage. The thing has accelerated upwards. It's gathered all this energy, rain droplets, ice crystals, snow pellets, frozen hang glider pilots, frozen birds, frozen insects. All kinds of things get swept up in these clouds as they blow upwards. It billows up so high that it actually smashes, and the updraft smashes into the boundary between the troposphere and the stratosphere. It's called the tropopause. Think of it as a membrane between the lowest layer of the atmosphere called the troposphere and the next layer up called the stratosphere. It's an actual boundary. And that's what it smashes into. Let's go forward one. Okay, so the mature stage, all this energy is going up. It's just billowing upwards and accelerating upwards. When we reach the mature stage, that's the most likely stage when the rain is really going to cut loose. Hailstones cut loose. Lightning is going now. Strong winds and atmospheric vortices are all happening in this mature stage as you transition from the cumulus stage to the mature stage. Now, the real characteristic of the mature stage is all this energy being released, and there's updrafts and downdrafts going on inside the cloud as the thing is getting ready to overbalance itself and reverse. And this stage, the anvil top is prominent, dark color. We'll see some more examples of that. And this stage lasts from 10 to 20 minutes, but can be longer in that 10% of severe type storms I was talking about. The typical thunderstorm is 30 to 45 minutes. The big bad ones can go several hours. All right, let's move forward one. All right, so in that mature stage, updrafts feeding one side of the storm, downdrafts now coming out. And notice that as the updraft billows up so high, it flattens off on top. I'm sure we've all seen that, the classic anvil top shape of thunderstorms. Why do they do that? They're literally crashing into the stratosphere. There's a layer up there called the stratosphere, and it's an impermeable, well, nearly impermeable layer to clouds. It's like a wall. It's a lid, so to speak. And it billows upwards so much that it flattens off and spreads outwards, creating the classic anvil top shape. And the energy, instead of going, it can't go up anymore, so it goes outwards. Oops. Let's go forward one. All right, so the mature stage is updrafts, condensation, and then the condensation gets so big and so heavy, the hailstones, the rain droplets, everything eventually gets so big, the updraft can't support it anymore. And now it reverses itself. That old adage, what goes up must come down. And that's exactly what we're going to see as we start into the mature stage. Go forward one. All right, so if the rain and hailstones are too heavy to suspend, at that point, the precipitation cuts loose with a vengeance. Let's go forward one. Okay, so mature stage, flattens off, hits the stratosphere, maybe 30, 40, sometimes 50,000 feet up, way up high, tens of thousands of feet, several miles. And at any storm that's powerful enough to lift all that moisture at 50,000 feet high in the atmosphere, the amount of energy being released is equivalent to that of an atomic bomb. It just takes an hour or so to release its energy rather than a few seconds. But that's the kind of energy that we're talking about. So that's the mature stage. Let's go forward one. Okay, and it's being fed on one side of the storm or the center of the storm, the core of the storm by 100-mile-per-hour updrafts and a fully developed Oklahoma-type thunderstorm. Let's go forward one. So there it is in time lapse. You can see the updraft billowing in the tower, feeding in with moisture and heat that's channeled upwards, and then it smashes into the stratosphere and spreads out. Can't rise anymore, so it spreads laterally rather than upwards. It's an impressive beast. All right, let's move forward one. So I just love photos like this because it looks like one of those end of the world movies. You know, I mean, like aliens are about to appear, or a comet is about to hit the Earth, or something like that. This thing has got a lot of energy. It's an energetic beast. It's being fed by an optimum combination of all the things I've been talking about: low-level moisture, heat, billowing upwards, lifting mechanisms, atmospheric instability have all come together to create this beast. All right, let's go forward one. Here's a mature stage thunderstorm over the Pacific Ocean, photographed from the International Space Station. The astronauts up there love to take photos looking down, and they catch these beautiful photos of sunrises and sunsets and thunderstorms from above. In fact, the first one to really remark about thunderstorm activity was John Glenn when he circled the Earth in 1962. The scientists were asking, can you see lightning? Can you see thunderstorms? And he was like, yeah, look like firecrackers going off out there. And looking down, especially at night, you can see that happening. So you can see that it's being fed by updraft towers going on in there. I think my batteries are now. But you can see it's also smashing into the stratosphere and spreading out. The thunderstorms over the tropical Pacific Ocean, because of all the heat and all the moisture, are the tallest in the world. They can go up to 50,000 feet or more. They're not the worst in the world. Those are over Oklahoma, but they are the tallest and some of the wettest out in the Pacific Ocean. I'm not saying thunderstorms over the Pacific Ocean are gentle. I'm not saying that. I'm just saying the ones over Oklahoma are worse. Let's go forward one. So, reaching 50,000 feet of altitude, even military and commercial aircraft have to divert around those things. Trying to fly over them is a risky business, especially over the tropics. In fact, several serious aircraft losses have occurred over the Atlantic and Pacific Oceans by pilots trying to fly over the top of building thunderstorms during the building and mature stages. The Air France crash about 15 years ago was a prime example of that. All right, let's go forward one. Finally, we reach the third stage, dissipating. And at this point, everything is now reversing itself and heading back downwards. This is the dissipating stage, and its characteristic is downdrafts only. No more feed. It's all exhaust now. Go forward one. Okay, so the cloud bottom is collapsing. It's all downdrafts, and now the winds get strong, right? Because they're going to transfer, not only being in the horizontal direction, or the vertical direction, they're also going to be in the horizontal direction when they hit the Earth. Rain gets really heavy and then it slows down as storm dries out. And the lightning, which reaches its max at the transition between mature and dissipating, begins to dissipate at this stage. Let's go forward one. So that's the point where the bottom drops out. Seen from a distance, it's fairly easy to identify. See, the bottom is dropping out of these cumulonimbus clouds, and it's all downdrafts feeding downwards in the dissipating stage. Let's go forward one. There's seen from a distance, it's better. When you're right underneath it, it's hard to tell. But seen from a distance, you can see the collapse stage a little better than if you're right underneath it. You'll feel it if you're right underneath the storm, but seeing it is a different matter. Go ahead, one forward. So there it is in the collapsing stage, the dissipating stage. And what I want to remark upon is the fact that all this raindrops and hailstones and all the stuff that's been suspended in a cloud eventually gets so heavy and cold that it plummets out of the bottom of the cloud, carrying air down with it, cold air down with it. And it helps equal as the temperature imbalance between the lower atmosphere and the upper atmosphere. Recall I said earlier that a key component of instability in the atmosphere was a warm layer of moisture at lower altitudes. If it's too warm and it's too moist, the atmosphere will flip the script. It will take the warmth and send it upwards and take the cold and send it downwards to balance the two. And that's all weather really is an attempt to balance warm and cold air masses, either in the horizontal or in the vertical direction. But the main thing to pay attention to is as that downdraft, sometimes called a downburst or a microburst, hits the ground, it spreads outwards in all directions with a vengeance. Let's see. Go forward one. Okay, 100-mile-per-hour downdraft. We had 100-mile-per-hour updraft feeding it. It's only natural we get 100-mile-per-hour downdraft coming out of the bottom. Let's go ahead one forward. All right, so here's a wet microburst full of rain hitting the Phoenix airport 2 years ago. Watch. And then not only is the rain extremely heavy in the downdraft, but watch the wind skirting in a horizontal direction. 100-mile-per-hour winds transferred from the vertical direction in a horizontal direction. That's called a downburst or a microburst. They are much more common and much more destructive than tornadoes. All right, I say they're much more destructive than tornadoes because they happen a lot more frequently than tornadoes. Tornadoes are rare events. They're dramatic and they cause a lot of damage, but these types of downbursts, these cause a lot more damage pound for pound than tornadoes do because they're much more frequent. All right, so that's a wet microburst, and that's the type of thing where you can collect an inch of rain in 20 minutes. I mean, underneath a collapsing thunderstorm cell. Let's go forward one. When thunderstorms collapse like that and they create 100-mile-per-hour downdrafts and 100-mile-per-hour lateral winds, it can play havoc with aircraft, sea kayakers, sailors, firefighters, transportation, cars, trucks, airplanes, trains. All these things can be affected. So this is an example of a downburst that hit an ongoing regatta in Mobile Bay, Alabama. Let's go one forward. This is what it looks like when a microburst hits. You go from dead calm into wind gusts 50, 60, 70 mile per hour winds or more in just a matter of seconds, like that. That's why people get caught by surprise. Right? You got the sail set up, you're going one way, and all of a sudden the wind reverses, and you get hit with 70-mile-per-hour gusts. It flipped the boat over, and it does happen. And in fact, this is indeed what happened. Maybe 4 fatalities at this regatta in Mobile, Alabama. Plus the poor visibility, the extremely heavy rain, choppy seas, and everything else contributing. Let's go forward one. Okay, so this was a gust front from a dry microburst that hit Phoenix just a couple of days ago. We're going to see some photos of that. Go ahead, go forward one. So dry microbursts are the same beast. It just, instead of coming with a lot of rain, it just comes with a dry downdraft. The rain evaporates before it reaches the ground, and it spreads outwards in a concentric ring in the impact zone underneath the center of the storm. All right, so these are called gust fronts or outflow boundaries as they spread away. It's like a blast, shockwave from an atomic blast. It spreads outwards like that. And that's what contains the very strong winds. As that concentric ring spreads across the landscape, you go from dead calm to 50 or 70 mile per hour wind gusts or more in just a matter of seconds. Let's go for one more. So there it is, hitting Phoenix just a couple of days ago. And it creates a downdraft. It creates a dust storm, also called a haboob. That radiates outwards from the center of the impact zone underneath the center of the storm. Extremely strong winds and poor visibility. Okay, so here, the same Phoenix airport, not getting hit by a wet microburst. Instead, it is getting hit by a dry microburst and creating the same kinds of effects, but just with dust rather than rain. All right, so when a microburst hits, expect the winds to kick up strongly in less than a minute. Let's move forward. So the typical thunderstorm lifespan, 30 to 45 minutes. Cumulus stage, towering cumulus stage, mature stage, and dissipating stage. It's just all one big indraft, inhale, and a big exhale. That's the classic type of thunderstorm, 30 to 45 minutes. Now, there are different types of storms. The severe storms that I'm talking about don't necessarily follow this rule. Severe type thunderstorms tilt, they lean over, and they don't necessarily last only 30 or 45 minutes. They can last for several hours. If we had more time, we could go into the dynamics of severe thunderstorms, if we don't have it tonight. Let's go forward. Let's talk about lightning. All right, so move forward. Lightning, by definition, occurs with all thunderstorms. Costs more than $1 billion in insurance losses globally because of all the damage that lightning does. Causes an average of 20 to 25 deaths in the United States yearly. And that's down from about 40 to 50 deaths per year about a decade or more ago because of better education and awareness and some of the new technology that helps people stay better aware. Let's move forward. And I hate to break this to sea kayakers, but there is no safe place outside when there's thunderstorm and lightning in a vicinity. People ask me, where's the safe place to go? If you're outside, you're at risk. All right, so let's talk about some of the risks and how lightning forms. So lightning begins in a mature stage, and the characteristic of the mature stage is the updrafts and the downdrafts concentric at the same time. You got to have that shear going on, updrafts and downdrafts going on. And the second ingredient, not only updrafts and downdrafts you got to have going on, but you must also have a combination of frozen ice crystals that get high enough to freeze in the atmosphere and water droplets or semi-frozen water droplets that haven't quite completely frozen yet. So you got to have both. That's called the process of glaciation. The storm has to get high enough in order for freezing and glaciation to occur. So you've got updrafts and downdrafts going on. Let's go forward one. What's going on inside there is these snowflakes scrape alongside the water droplets or the semi-frozen water droplets. And it's the contact and scraping in between the two that separates electric charge in a manner very similar to this. Let's go on forward. What happens if you scrape your feet on a nylon carpet as you walk around a room? You reach for the nearest doorknob or you shake somebody's hand, what happens? Zap, right? You've scraped off electrons and created a static electricity charge. It's the same within a thunderstorm in a mature stage. It's just happening in a vertical direction rather than the horizontal direction. Let's go forward one more. So what winds up happening is in the mature stage is that because of the scraping effect and the separation of electric charges, positive charges get sent up to the top of the cloud. And the negative charges tend to sink down toward the bottom of the cloud. In effect, the cloud becomes a charge separator or an electric capacitor, storing electric energy at the top of the storm and the bottom of the storm. It's charge separation. Let's go forward one. So there are three main charge zones in a thunderstorm. The high altitudes up in the ice crystals way up there becomes positively charged. The center and bottom of the storm becomes negatively charged. Let's go ahead and bump forward one, two, and then down at the bottom near the surface of the earth, because the negative charge in the center of the storm becomes so strong, it actually attracts positive charges near the surface of the earth to gather underneath the center of the storm and follows the storm as it roves across the landscape. Now that's in opposition to what we normally think of the Earth as being a negatively charged surface. When thunderstorms are in effect, the surface of the Earth becomes a positively charged surface in opposition to normal electric polarity. And that's the reason that the strong separation of electric charges causes things like compasses and handy-talkies and electronic devices to start acting a little haywire if they're subject to extremely strong electric fields that happen underneath thunderstorms or in thunderstorms. All right, so let's go forward one. Most of the lightning strikes that happen in a thunderstorm are relatively weak strikes that happen within the cloud, equalizing the positive and negative charges at the top of the cloud and the bottom of the cloud within the cloud. These are frequent, but they're relatively weak in comparison to the other types of strikes. Let's go forward one. Okay, so that's what we see within cloud strikes. You see the cloud light up. We don't see any stroke of lightning underneath. So it's an in-cloud strike, and those are relatively frequent events. Let's go forward one. Now, more commonly observed by human beings, let's move forward one, is what's called a negative strike that occurs underneath the storm and then equalizes the imbalance between the negative charges in the storm and the positive charges underneath it at the surface of the Earth. When the imbalance of charges becomes strong enough, something's going to give. Something has got to give. Let's go forward one. So what winds up happening is that the cloud sends down weak feelers of energy called stepped leaders of negative charge in 50-meter increments in microseconds, coming down from the cloud bottom, seeking the path of least resistance to the surface of the Earth and the positive charges underneath. So we get these negative stepped leaders that work their way downwards, increment by increment in milliseconds. All right, those are called stepped leaders. So here's what it looks like in slow motion. Stepped leaders coming down. They're all looking. Where's the path of least resistance? They're going to try to find it, and they're going to get some help. Let's go forward one, because at the same time, the positive charges gathered at the surface of the Earth sense the approach of the negative charges working their way downward from the cloud above. And they're going to start trying to do the same thing in the opposite direction, seeking the path of least resistance going upwards. These are called streamers coming up from the surface of the Earth. Let's go forward one. All right, so a full lightning flash in slow motion, step leaders, negative charge coming down. Here comes the positive charges coming up. Boom, found the spot of least resistance. And that's where the charge imbalance equalizes itself with several return strokes. There it is, one. Okay, so this one I think has 3 return strokes. Step leaders coming down. Positive 1, 2, 3. Okay, let's go forward 1, 4. Multiplicity, the number of strokes per flash is called stroke multiplicity. A flash is just a big boom that we see, the big flash that we see. The multiplicity is the several return strokes that we see flickering within. All right, typical Oregon thunderstorm, 2 or 3 return strokes, sometimes a little bit more. Over Texas and Oklahoma, 7, 8, 9, 10 sometimes, powerful strikes. Over Brazil, they're up to 35. They've been finding 35 reversals. All right, so let's move forward one. So at normal speed, boom, there it is. That's what the human eye perceives, is that flickering effect. So the flickering effect that the human eye perceives is the return strokes, positives and negatives going back up and down that channel. That channel is only as wide as your thumb. It's very narrow, but there's a lot of energy concentrated within it. Let's go forward one. Okay, so here it is in slow motion, step leaders coming down. And then bang, found the spot. There's the power strike right there. Stop motion photography is wonderful because you can see these things. All right, let's move forward one. So, like I say, low multiplicity strikes, 2 or 3 reversals. That's pretty commonly what we see here in Oregon. Not very strong thunderstorms. 2 or 3 reversals. All right, so let's move forward one. And then there are the high multiplicity strikes that reverse several times in that channel, expending a lot of energy from different portions of the storm down that channel, that path of least resistance. So let's go ahead one. So that's the kind of thing we're watching for, is that massively flickering effect. You know, you got a powerful storm when you're seeing that kind of thing going on. I mean, has anybody here ever been to the Texas or Oklahoma style thunderstorm? Yeah, you know what I'm talking about. I mean, it is something else. All right, so let's go forward one. And then there are sometimes that the energy imbalance becomes so strong and the reversal of strokes is so frequent that it creates what's called a continuous current. It's basically like draping an electric wire from the sky down onto the surface of the earth. Whatever is underneath it is going to absorb a lot of energy in a short amount of time. These are the ones that cause fires. These are the ones that explode electric transformers. These are the ones that kill people. Let's move forward. All right, so there's a high multiplicity strike. Coastal California.
Is it striking?
Let's go through that. Let's go move forward one. So people ask, what happens to the fish in the water when there's a high multiplicity strike? And the answer is the positive charge is gathered only at the surface. And so the charge equalization occurs only at the surface. Just a few feet down, it's a relatively safe place to be. So that's why we don't see tons of dead fish floating around after an intense thunderstorm, because they're safe a little bit further down, but it's the surface is a bad place to be, like where an ocean kayaker might be floating around. Okay, so notice that the charge not only is coming vertically, it separates out horizontally. So the lightning strike essentially becomes a horizontal event, in addition to being a vertical event as well. So you don't want to be in a sea kayak, because a sea kayak is a long relative transmitter of electric energy. Let's go forward one. There's other. So the other danger, of course, is the fact that these streamers exist near the surface of the earth. Even if that electric pole, that flagpole, that construction crane, even if it doesn't actually get hit by a stroke of lightning, there are still streamers that come off these things. In fact, I recall speaking to a group of mountaineers who were climbing Mount Rainier some years ago, and they could feel the electric charge in their bodies as a thunderstorm went over the top of them. And they would all drop their tools and get down into a squatting position as the storm went over, and the strikes were going very, very close to them. And they could literally feel the streamers coming off. And we'll see a dramatic photo of that coming up here shortly. You can be killed by streamers. You can be injured by them. Even if you don't actually get hit by the strike, the energy in nearby streamers can be sufficient to kill a human being. That's why I keep saying there is no safe place outside when lightning is striking. Let's move forward. We want to avoid any long electrical conducting objects like electric wires. Stay away from those things as far as you can, because they're just going to conduct the energy. They'll attract it and they'll conduct it. Fences are another good example of that. All right. Stay away from fences, because it's just an electrical conductor. And it'll take that vertical lightning strike and just turn it into a horizontal lightning strike. That much easier to do. Let's move forward one example. All these cows sticking their heads through this barbed wire fence, eating the grass on the other side of the fence. Lightning hits the fence and killed something like 35 cows in one fell swoop because of the transmission of energy through that fence. Good idea to stay away from trees. Hard to do in Oregon, but it's a good idea to stay away from trees. Because trees, well, you think of like what happens like during these pro golf tournaments. Golfers are out there playing, crowds of people watching, thunderstorm breaks. What does everybody do? They run underneath a tree. Right? Let's get out of the rain. Bad idea, because it's going to attract that lightning. And not only does the tree attract lightning, but it's also likely to explode from being hit by lightning, because the sap and the water inside the tree boils and explodes. It's great shrapnel. Go ahead, one. So another animal and trees then also can create side flashes as well. The energy just decides to leave the tree and go through the nearest animal or human being. Instead, who can predict what all that energy is going to do? Let's move forward. Same thing, all right? All that energy, shrapnelized bark and wood flying off it, and all that electrical energy. Kill all these sheep in South America. Don't lay down, okay? Because when lightning hits the ground, just like it hits the water, it spreads out laterally. When it hits the ground, it also spreads out laterally. So laying down is a good idea. Experts recommend getting into the lightning safety position. Change your body shape from being a lightning rod into an insulator. If you get hit by a streamer or an actual strike, you don't want the energy to go through your nervous system, spinal cord, and your brain and your nervous system. It's better to suffer burns on your skin, which are relatively tame compared to the nervous system damage, than if you take a direct strike and it goes through your spinal cord. Most people who die from lightning strikes are not from burns, it's from nervous system failure, nervous system damage. Oh, yeah, here we go. So let's move forward one. All right, so that's what it looks like. Energy just dissipates laterally. Go forward one. So the ground current, oh man, this poor guy is having a bad. Does the lightning safety position work? I volunteer not to be the one to find out whether it works. But what I'm told is that nobody who's been in the lightning safety position has ever been killed by a strike. People have been singed and burned, but not necessarily killed by lightning strikes. Maybe good luck, or maybe it works. Let's go ahead and forward one. So, the Weather Service advises people when thunder roars, go inside, go indoors. They like to recommend the 30-30 rule. 30-30 rule is when you hear 30 seconds between seeing a flash and hearing the boom, 30 seconds or less, that's time. That means it's time to go in. That means the lightning's 5 or 6 miles away from you. Time to go inside. And wait till about 30 minutes after the last boom or flash before you go back outside again. Let's go forward. We're running out of time. We'll finish by looking at positive strikes. I described the negative strike that comes out of the bottom of the storm with the step leaders and the streamers that meet and create a lightning stroke. There's a different type of flash that is more rare, but it's more dangerous. It's called a positive strike. And that's what happens when the positive charges up at the top of the thunderstorm cloud, way up high up there, get lonely. And they decide they're going to equalize with the surface of the earth at some distance away from the center of the storm. This may be 4, 5, up to 10 miles away from the center of the storm. So that lightning strike from a positive strike reaches out laterally from the top of the storm and then down to the earth, right? They're few, but they're powerful. Any strike that can go that far away from the center of the storm and then downwards is a powerful strike. Let's go forward one. Okay, so negative strikes, positive strikes. Let's go forward one. That's what they look like coming out of the side of the cloud. They come by surprise. You may think you're safe. You're 10 miles away from the nearest storm. I'm safe, right? Not necessarily. Those positives, they also called a bolt from the blue. Positive strike coming out of the side of the storm. Go ahead one. Let's go ahead one more. There it is. That's the photo I'm looking for. All right. So if you're in the zone where the positive charges are building up and that charge buildup is occurring, if your hair stands up, if your handy talkie or your a metal tool you're holding starts to flare off sparks of electrical energy, say an Elmo's fire, it's a good idea to drop the tool and get into that lightning safety position. This photo appeared in National Geographic magazine in the early 1970s. I remember reading it in my grandfather's basement. And these two people were standing on a ridge top in Colorado thinking they were safe in the nearest thunderstorm, which was miles away. A few seconds after the photo was snapped, the photographer was hit and killed by a positive strike that occurred. Okay, so I think we're just about out of time, so we'll call it quits at this point, and we can do some questions. All right, so we sure will. So let's do the first question right here.
If we take lightning out of the equation, what you describe in terms of dynamic of the building up and the downdrafts and so forth, my understanding of meteorology is that the downdraft and the gust front out on open water is characteristic of the squall.
That's right.
And that is, you know, something that if we're sea commenters, when we see that gust front approaching, it can be rather rapid, and that's something that would be a place I'm sure as I wouldn't want to be, you know, in the line of that gust front coming out. I just wanted you to address that.
Certainly, yeah. And over land, we call it a microburst or a downburst. Overseas, it's just called a squall. That's the same thing. And it's spreading out laterally. I have a suspicion that what we call the Bermuda Triangle probably is an area where there was a lot of that kind of thing going on. Ships, aircraft hitting squalls and being lost out of it. There's another theory about the Bermuda Triangle, which also says that it's just such a busy place. You're naturally going to have a lot of lost aircraft and boats out there as well. But yeah, squalls, absolutely. It's just a downburst over the ocean. Best thing to do is head into it, straight in.
Actually, 3 questions briefly. One is, if you avoid the open, but you avoid the trees, where do you go?
Yeah.
2, why 58 miles an hour? What's interesting about that number? And 3, what is the surface condition when you have these 100-mile-an-hour updrafts? Are you getting sucked up yourself, or is there a layer of change between the surface where the updraft is occurring above?
Yeah, so let's go back. We'll answer those in reverse. The first question is
Conditions on the ground.
conditions under the ground with 100 mile per hour updraft. Most of the updraft that feeds into a developing to mature stage storm is coming not from the ground itself, but in the column underneath it. Although there is a special case where there is air from the ground going straight up into the storm. And that special case is called a tornado. Yeah, exactly. Yeah. But otherwise, right off, it's unlikely a person is going to be lifted off the ground, Dorothy and the Wizard of Oz style, and, you know, be wafted off into a storm. But the downdraft, it does hit the ground and spread out in all directions. Secondly, where's the safe place outside? If being near a tree isn't safe, and being out in the open is not safe, what is safe? There isn't any safe place out there. I think in such a case, I might choose the forest rather than the open, because at least there's a lot of trees and they're not necessarily all going to get hit. Just hope the one that you're underneath doesn't get hit, I think, is the best way I can put on it. I've heard of people getting hit in all kinds of circumstances, underneath trees, out in the open, crouching in caves, being drenched by rainwater and then lightning hitting the water and electrocuting them through the water as well. There's just no safe place. Best place to go is inside a house if possible, or vehicles are good places to go. If you can get into a truck or a car, that's a good place. What was the third? I think it has to do with the conversion to metric, meters per second or kilometers per hour. But yeah, because I don't know either.
Can you give us kayakers advice as to when to seek shelter or what to do?
Yeah, I like that weather eye on the sky, watching the buildups of the clouds. Well, reading your weather forecast first for the area that you're interested in, where you're going kayaking. And by weather information, I don't mean the iPhone app that has a sun or a moon or a windy symbol on it. I mean getting a hold of the direct information from the National Weather Service, who your tax dollars have paid for, and they really do spend a lot of time putting a lot of detail into their forecast for particular areas, including any weather warnings that are in effect, which would include strong winds and it'll say, when I get concerned when I start hearing chance of thunderstorms. All right. And the reason I say that is because most of the time there aren't thunderstorms around here. You're just not going to read it in your forecast, particularly out at the coast. I mean, how often do we get thunderstorms at the coast around here? Once a year, maybe. But if you start hearing about lightning potential, threat of thunderstorms, 20% risk, 30% risk, that's when my warning meter starts going up, saying we're way above what the average conditions are. And I'm going to use caution accordingly. The other thing that I teach wildland firefighters is, yeah, we have a lot of cool technological tools, many of which we can carry in our pocket to observe and even make short-term predictions about what the atmosphere is going to do. But the only two observing devices that I have used that have been proven to be completely fail-safe are these right here, right? Keeping a weather eye on the sky. I'd sure love to come back to this group and do one on cloud types and weather associated with different cloud types. That's because that's a really good one to pay attention to. So paying attention to the weather forecasts, weather warnings, and then also what Mother Nature is telling us at any given time out on the ocean. Does that help?
Question from chat
Chat.
says, why does the stratosphere prevent storm from going higher?
Yeah. Okay. So why does the stratosphere prevent for vertical development of thunderstorms? The higher the stratosphere is, the further upwards storms can build, but eventually they reach that limit and they stop and they flatten out. What's going on is that inside that building cumulus cloud, it's hot in there. There's a lot of energy being released by condensing water. Now, when I say hot, I mean hot in comparison to the temperature inside that building cumulus cloud is a lot warmer than the temperature in the free atmosphere outside the cumulus cloud. As long as the temperature of the air inside the building cumulus cloud is warmer than its environment, it will continue to build upwards. It stops because that layer up in the stratosphere, believe it or not, is a very warm layer. It's a warm layer of air up there. And so the cumulus cloud is no longer warmer than its environment when it runs into a warm layer in the upper atmosphere. Therefore, it loses its potential for gaining any further energy. Now it's 50 below zero up there. I mean, it's really cold, but all we're trying to do in forecasting is compare what is the temperature of the air inside a cumulus cloud as opposed to what is the temperature of the air outside. As long as the cumulus cloud is warmer than its environment, it'll keep building. It stops when it hits the stratosphere, which is a relatively warm layer in comparison. It's an interesting feature, but the stratosphere is a upper limit of the extent of weather systems from the surface of the Earth. That's why jet pilots like to fly up there. It's a much smoother ride usually up above the clouds. I mean, commercial and military pilots, they turned a handstand when jet engines came around because they no longer had to fly through the cumulus clouds. They could fly in a stratosphere above them and get a much nicer ride.
So, water, I think it's water. How far does it go from its dissipation down to the cloud?
You know, I was afraid someone was going to ask me that. I don't know. I'll try to find out. I don't think it's very far. Yeah, it does eventually dissipate. Otherwise, we would hear more examples of injuries and or dead fish or whatnot around it. But I don't think it's very far. I'm thinking maybe 20 or 30 meters at the most. But I've also heard cases of people walking down a beach in Florida. Their feet are wet, the sand is wet, lightning hits a mile down the beach from them, and they jump up because they got shocked in the soles of their feet by the electric energy transmitting through the wet sand. No, it won't.
So we put this slide out.
They're good, yeah.
If someone like me that doesn't have knees that can go in that position, what is the second best
I
option?
think I'd sit on my butt. Yeah, to turn into a ball. The idea of turning your body shape into a ball and minimizing contractor count. If you got like a ground pad, a sleeping pad, that's a good thing to get on.
If you have like your phone or keys or metal stuff, should you like ditch it?
Yeah, ditch them. And the reason metal jewelry, iPhones, with the corded iPhones, you want to get rid of those, not because they'll attract lightning, but because if you do get hit, they're going to conduct energy and burn you. And I have some gruesome pictures of people with burns on the sides of their head from getting hit or being just near where a streamer hits and having their skin burned as a result of it. I just didn't have time to get them all in there tonight.
Awesome presentation, John. Hey, a lot of this focuses on severe weather. A lot of our weather isn't severe. It's still weather, but not severe. Can we make a rule of thumb judgment call? No problem on those days?
It depends upon how you define severe. I mean, being out on the open ocean, you're subject to wind, you're subject to swell, you're subject to local wind chop, or some wicked combination of all of those, especially if they're again, going against each other or at right angles to each other. That's another presentation I could do here is about local West Coast winds and how they form and how they evolve and how to predict them and how to analyze what's going on with them. That's a fun one to do too. It's one of the series of classes I teach at the Gladstone Community Adult Education School on Thursday nights. It's about winds and West Coast weather. Yeah, but yeah, there's all kinds of things. There's a wealth of information out there. I mean, if I could say that one thing I've seen in 40 years of doing this kind of work is when I began in the mid 1980s, we were literally pulling facsimile charts off of printers and coloring them with crayons and hanging them on pegboard that's left over from the Korean War in the weather office. And that was the height of the technology that we had. We got a satellite picture once every 90 minutes, black and white picture. This has 1,000 times more communication and display technology that I can carry in my pocket now than we had in the best weather offices back in the early 1980s. We've gone through a renaissance in gathering and transmitting and observing weather information and making it available to people. This is a whole nother night topic, how to get the best weather information out of your iPhone and how to interpret it, particularly when it comes to strong winds, thunderstorm gust fronts, squalls, and the like. You can use this tool to help yourself stay safe.
Wow. That was amazing. And yes, this has been recorded. So it'll be up on the website as soon as we get it all figured out. But gosh, John, thank you so much. Wow. Just a quick, we're over time a little bit, but again, thanks to Lucky Lab. We do have a program scheduled on September 24th. That's going to be Tim Matson. And I guess it must be my inner engineer or recovering engineer coming out here, but he's going to be talking about science and kayaking and the pursuit of happiness, like water, gravity, quantum mechanics, physics. Yeah. So we'll be posting that up on the calendar soon. Check out for that. And again, thank you so much for John being here. It's been fantastic. Bye, everybody.